Do you want to learn how you can add full text search to your application completely serverlessly? In this video, that is exactly what I'm going to show you how to do. Now, Amazon does have its own serverless Elasticsearch service, and honestly, I think that's completely bogus. Even though it says it is a serverless service, you have a minimum price every month, and it's more like a managed service like RDS. So in this video, we're going to focus on building a truly serverless free text search functionality using AWS Lambda and API Gateway. So this all started when someone sent me this article about full text search using Lambdas and storing the data in EFS. This is a really interesting article, and if you scroll through, basically what he does is he uses this package called Flex Search. And what happens is when you save a set of data into your Flex Search, it stores it into EFS. And then when you do a query, it gets that same data from EFS and then queries upon it. And the logic is relatively simple. I thought this sounded amazing, so I wanted to try it out for myself. My issue was when I went and actually tried to create the add records and the querying using Flex Search, I could create the indexes and I could search on them inside one Lambda, but I wasn't able to persist them into EFS in the way the article had. I found out later that this was because there was a new version of that Flex Search library which changed the way that it stored data, which meant you can't persist it to EFS anymore. I still really like the idea, so I decided to try out a couple of different libraries out there to try and find one that does work. I tried one called Luna, and then finally found one called elasticlunker.js, and this is the one that I found works most effectively for this use case. Obviously there may be better ones out there, and even if you go to another language, you could design this similar architecture in Rust or something else, and it could perform even better than this. But what I'm going to do now is kind of talk you through how it works and basically explain some of the updates and then some of the testing results that I've found. So if we go through, what you do is you basically create an index, and this index is an index of Elastic Clunker, and you say I want there to be an ID and a text, and these are the things that you can search over. If you wanted, you could have multiple different fields, so you could have the description, you could have other meta tags inside your index, which means there would be more data for you to search on, but that would also mean that each row in the index is larger, so would take up more data. So for this, I just went with searching on the name of the products, or in my case, text. Now, the next thing I wanted to do was to actually be able to update an existing index. So what we need to do is we need to get an existing record or an existing index that we want to add onto. And in this case, we want to get it from EFS path and then product names. And if you look at the top, I have this in an EFS mount path, basically saying that we will have an EFS volume attached to this Lambda. And I'll talk about how I've done that a little bit later on. But we can basically read that file and then load it in. And then if that JSON data is a valid set of Elastic Clunker JSON data, then what we can do is we can load that data into our current index. And then what we do is we map over each item that I've sent up via this add records API and add them also to the index. Finally, we turn it into JSON and write it back to EFS so that we can basically read it in another Lambda. I also added this little bit on the end just so I can do a self search. So I pick one of the items and I do a search on it to see if I've got anything back. This just means that when I do add a record to our set of data, I can see was I able to find one of those records inside the data. If not, I suspect something's gone wrong. That is adding a set of records. And now if we go down to query, now this is going to look very similar. You get the index, you've got our EFS path, and you read the file from EFS into the index data, and you load that data into the Elasticon index. From here though, it's slightly different. What you can do is you get the query, the limit, the options, basically the parameters of our event. And then what we do is we pass those into index.search, and that gives us the result. And that result can be passed back into our format JSON response, which returns our API request. So in Postman, we have our API request, and we can pass up our data with the ID and the text. And that is basically all we get. Now, if we copy something like Alicia Solid, what I'm going to do is I'm then going to also open up the search request. And in here, I'm going to change this to Alicia Solid and hit send. This will then get our EFS store and it will turn our data. As you can see, we have got a set of results, and I'll just make this a little bit bigger. And if we actually look, we have, wow, there are 6,900 rows between here and here, so that's probably, 200 records that match those results. The query is that, and we can see that we actually just queried over 420,000 different records in our index. So that is querying and searching. So one other thing I thought could be done and would actually speed up this process a lot is if we actually cache our data. Now, this is because one of the longest processes in here is actually reading the file and then loading it into our index. Instead of actually doing that, what we could do is we could either cache this index or cache the index data inside a global variable outside of our handler, so that on the second request, we don't need to go and fetch that. So that's exactly what I did inside query names cached. Now here we have a variable outside of our handler with data and a refresh. And what we do is when we get our request, we check if the cache refresh is further in the future than now. So basically, if we don't need to refresh the data yet, then we can just load the data from cache.data. If we basically don't have a refresh date, or if the refresh date is behind us, then we need to get the data from our actual EFS data and load that in instead. Once we actually load our EFS data, we can set our cache to have the currently loaded data and set the date for the refresh to 1 hour's time. So in an hour, it will have to redo this process. And that just means that your data doesn't get super duper stale if you've added records that won't appear inside the cached data. After that, basically it's going to be exactly the same. It's creating your search and formatting and sending that back to the user. So I've actually done a load of testing with this. So I want to talk through the results. So as you can see, when doing a normal query on varying sizes of indexes, the time to do the request varies. Obviously with cold starts, it does have a noticeable effect, going from 309 milliseconds for a non-cold start to 929 seconds with a cold start. And that is in part because we are inside a VPC, and that is because that is how you have to attach a lambda to the EFS volume. So as you can see here, 309, 301, sometimes down to as low as 198 milliseconds. And then if we increase the index size to 20,000 records, it's taking more like somewhere between 623 is the lowest, all the way up to 947 milliseconds, so still under a second, as long as it is not a cold start. We can then take things even further, and if we add something like 220,000 records to our index, we can now see that we are taking somewhere in the vicinity of 3 to 5 seconds. If we increase that further to 420,000 records in our index, it's taking a response between 8 and 11 seconds to return this data. And as we can see, I also started tracking the amount of memory we were consuming. So we are actually consuming 700 megabytes, 800 megabytes of memory at 420,000 records. So if we carry on adding records, we would hit the memory size limit. All of these tests were done with a 1024 megabyte lambda. So obviously if you increase the memory capacity on your lambda, you would also get an increase in CPU power, which might even decrease these values. But for now, if we went past 420,000 records, we'd likely hit that memory size limit. Now, obviously, I talked about what happens if you cache the data. So here I have the same results, or the same queries, but run on the cached data. So the first time it does a query on 3,000 records, it takes just under a second. But the second, third, fourth, any future requests, even if you change the actual query and query on a different record, they start taking 62, 38, 45, 49 milliseconds. So these times are really rapid and are significantly better for any functionality we want to do. Now, you must keep in mind with cold starts that although this is a significant difference, the percentage of times if you're running a production workload with consistent traffic, the amount of times you'll actually see a cold start will be very minimal. I think we've calculated it before to be less than 0.1% of the time. So if we then increase the records up to 20,000, again, you can see there is a notable increase in the amount of time for the first request, but second and third and fourth requests are actually very minimal. As you can see, that pattern then continues even if you go to incredibly large numbers of records, such as 420,000 records. We can see that the first one takes 11.2 seconds, but the second one takes 52 milliseconds, 43, 61. And this kind of proves that having that data cached inside your Lambda global variables can make an incredible amount of difference to both the performance of your responses, but also the amount of money you're paying. Here, you're paying for 11 seconds of a 1 gigabyte Lambda. Here, you're paying for 52 milliseconds. That is 215 times faster, and therefore the cost will be 215 times cheaper if you are adding caching versus if you're using the fetch on every single request, not to mention the extra data transfer costs there may be with EFS. Now, talking about adding records, if you add a single record, again, it's going to be like 61 milliseconds. Adding 3 records at a time, I found that with a cold start, it was 793 milliseconds. But after that, this is with very few records in our index originally. It was 79 milliseconds. Adding 1,000 records at a time via API is still possible. And you can see that even if there is a cold start, it takes just over a second. Getting up to where we have 2,000 records already in the index, this now takes 1.3 seconds to add. So obviously the time is kind of proportional to the number of records you're adding, as well as the size of the existing index. Now, another thing you might want to do is actually upload via CSV. So I've created in here a process CSV functionality, which just reads a record that has been dropped into an S3 bucket and basically transforms that, adds that to the index, and then returns the index that it generates. And that is another way of adding records, and probably a way that a lot more people would use. So in here, what I did is I tried to add 1,000 records when there's already 3,000, and it took 1.2 seconds with a max memory of 200 megabytes without a cold start. I thought that's fair enough, but what about 20,000 records at a time? So here, this took 7.28 seconds, and there were already 4,000 records in the database. And you can see here that I actually broke down the time it took to do this request. So processing the CSV file, which involves actually downloading the CSV file from S3 and converting it from that into JSON and doing a bit of mapping on the fields, actually took 4 seconds. Getting the data from EFS took 0.2 seconds. Adding the records took 1.8, and then re-uploading that new file took 0.7 seconds. So that brings up the total to almost 7.3 seconds. But since this is an async process, that's actually not too bad. So I thought I'd push it even further. I originally did try 1,000,000 records at a time, but that didn't work at all. And I'm going to zoom out one more so the table formats properly. And here we can see that I actually split it into 5 200,000 record files. Now, what happened was the first time I tried to add 200,000 records, it took 19 seconds and took a maximum memory capacity of 720 megabytes. Again, this is with a cold start, but it worked fine. And that is how we got some of these queries up here, where we have 220,000 records. That is 20,000 via API and 200,000 via our CSV upload. From there, we then added another 200,000, and this time it took 47 seconds. Now, this did work, but we know that we used the absolute maximum of 1024 megabytes of memory, so I wonder if there is some mechanism inside Lambda where it can offload some of its RAM into a more persistent storage, a bit like when your laptop or your computer does a swap and stores some of the data from RAM into more persistent memory. Because this succeeded but did use exactly the right amount of memory, and I think that's kind of somewhat unlikely. I suspect it may have gone slightly over and used this, hence swapping that data into a more persistent storage is why this took such a long time to run. Finally, when we tried to do it again, so there were 420,000 records already in the index, we tried to add another 200,000, and this did actually eventually run with a runtime exited error. This is most likely because the Lambda ran out of memory and couldn't do any more swapping, and I suspect this is the exact same cause as why we couldn't upload 1,000,000 records at a time. Now, obviously all of this has been done on a single Lambda with 1024 megabytes of memory, and you can go up to 10 gigabytes of memory. If you wanted to do that, you definitely can, and this could work, so you could even try adding 1,000,000 records at once, and then querying on 1,000,000 records with a much larger Lambda, and that's something I'm probably going to do right now, and then add this as like a PS to this video. But the aim of this video isn't to give you a proven solution that will work in every scenario. It's to kind of show you a pattern that is kind of really cool and a way of actually creating a genuine serverless free text or full text search that works without this Elasticsearch serverless, which is absolute nonsense. So if you want to use this yourselves, try it out and see how well you can use this in your applications. So now that we've looked at the results and the performance of this architecture, let's actually look at how we could actually build this architecture. So to start with, we have our functions, and our functions are pretty simple. We just have add record, add records, a query names. You could obviously rename that to just a query, and then our process CSV. And for our functions, we'll notice that if we look here at the query names, we have the normal thing, which is the handler and the event. But here we also have a VPC config, and that is because EFS needs to live inside a VPC, and therefore so do our lambdas. As well as that, we have a specific IAM role statement, which we'll look at in a second, and we also say that this function depends on the mount target. So that basically means that we can't create this lambda and its IAM role until we've created the EFS volume. So if we scroll up and look at the VPC config, we're basically saying this Lambda, and in our case all of our Lambdas, have access to the EFS security group, and it uses these subnets, and those subnets I've defined in our custom section because I've just used our default VPC instead of creating a separate one. For the IAM role, we need to be able to mount and actually access the Elastic file system. We also need to be able to use the create and describe network interfaces, as well as accessing S3 for when we do the S3 upload of the CSV files. So once we've got all of that, we can actually think about something else. At the moment on our Lambda functions, we've not described the actual EFS volume. Now, this may seem a bit strange, but inside the serverless framework, you can't just add as many different fields onto each of the records for a Lambda function as you like. For more customization of the actual definition of a Lambda function, there is something called function extensions. And basically this is a mapping saying, for this function name, add these parameters or these fields. So I have a separate file called function extensions, and we are basically going to map over every one of our functions. And then what we're going to do is we're going to create an entry where we have our Lambda function and we are mapping on these properties. And the properties are a file system config. This basically is how we're telling AWS that this Lambda function is going to have a access to this EFS. So we basically get the ARN from the EFS that we are about to create, and we say that this is going to be mounted locally at /mount/EFS, which, if you do want to change this, just make sure inside any of your Lambda functions you change that here as well. You could obviously make this a variable or an environment variable or something like that, and that would be another way of making it consistent. Finally, if we go on to our actual EFS, we have our file system, and this is just a general purpose file system. I've given it a name, and then we have a security group, and I've just kept this very simple and used our default VPC, and I've stored that in our custom variables, and then a mount target inside the subnet A, subnet B, and subnet C. We also have an access point, and then the EFS security group, which basically says, here's the VPC, and this is the security group I'm creating for accessing that VPC. And finally, we need to have a VPC endpoint. Now, this is because when you have your Lambdas inside a VPC, then if they need to access S3 or Dynamo, then there needs to be a VPC endpoint to be able to communicate out to those services from inside your VPC. So this is a gateway endpoint pointing to the S3 service, and I'm just using the region from our provider inside our main serverless config to define that, as well as defining that this is our VPC ID and here is the root table ID, so that it is able to map it from our current VPC out to S3. If you don't want to do the S3 processing, so that process CSV, then you don't need this VPC endpoint, and everything else will work via API. So if we go into our serverless TS, we can see all of our normal config. So I have used the serverless IAM role per function so that we can define our IAM roles inside the function definitions. And then if we scroll down, we can see that we have the resources of our EFS resources, but then we also have our extensions here, which are kind of the overrides for our Lambda functions that we were talking about earlier. Finally, in our custom section, we have our VPC ID, our subnets, and I've stored them both as an array of subnets because at one point we needed them, and as subnet A, B, and C, as well as our routing table ID. With all of that done, we can just deploy this, and this will deploy our whole config and our application so that we can actually do all of the testing that we've just done. Obviously, one thing you might want to do is inside your functions, you might want to change the memory availability on different ones of your Lambda functions if you are using very, very high numbers of records. So I have just now tested increasing some memories to 3000 megabytes and increasing the CSV processor to just 3 gigabytes allows us to process all of the records up to 1 million concurrent records. Even when processing the last 200,000 records, it only used 2.35 gigabytes of memory and took 25 seconds. With all of these 1 million records in our database, the original API did break, but increasing the RAM on that to 3 gigabytes as well still returns a response in just 11 seconds. Using the cached version of this API, I'm sure would give a very similar response with millisecond response times. In this video, we have built a truly serverless search functionality using API Gateway and Lambda, and this is something you can now apply into your own applications. This can be really powerful, as being able to search on just any text and get back the records that you need can be really powerful, but you can now do this without having to sign up to a serverless search service that costs over $720 every single month just to do the basics.